Hello guys, myself Sudeep Patil. Today we'll learn about how to convert binary to Oghams complement conversion. It's a very simple topic. We'll What is code conversion? Code conversion is in digital design refers to process of converting one code representation to another. Why do we need this? Because computer may not understand all the codes we write. It understands only certain codes. So sometimes we need to convert from one form to another. We do it by code conversion. Let us learn what are the different types of conversion. First is BCD conversion. What is BCD conversion? It is a binary representation of decimal numbers. We represent binary numbers in terms of decimal numbers. This is what BCD conversion is. Next is BCD to XS3 conversion. What is BCD to XS3 conversion? Here we add decimal number 3 to each binary number which we obtain. So we convert to XS3 conversion. Next is XS2 conversion. What is XS2 conversion? Here, it is highly encoded decimal representation. Here we had decimal 2 to each BCD digit. Conversion may be related when interfacing BCD based systems with XS2 based systems. Okay. First is BCD, next is BCD to XS3 conversion, finally is BCD to XS2 conversion. What we are learning one's complement, it comes under BCD conversion. Let us learn what is one's complement. Okay. What is one's complement? One's complement is another binary number obtained by talking all bits. That is, one's complement is also a binary number we used to obtain by flipping all the bits. That is, if we have, for example, if we have bit 0, what will we get by flipping 0? We get 1. So it is also a binary number, but we get it by flipping all the bits, transforming 0 to 1 and then 1 to 0. So it is a ones complement is a binary number which we obtain by flipping all the bits, that is 0 to 1 and 1 to 0. Here one positive numbers remain unchanged, that is in one complement positive number remain unchanged and negative number are counterparted to its counterparts. That is, if we have a positive number, if we do one complement, we get negative number, and if we have a negative number, for one complement, we get a positive number. Let us see with an example here. Name is represented as 1001. That is in 4-bit notation. If we have an 8-bit notation, we get it as 0000 and 001. That is, first 4 bits are insignificant. Significant bit is 1001. That is the 8-bit notation of 9. First, let us do ones complement. What we need to do, we need to flip all the bits. That is, if we have 0, we need to flip it as 1, and if we have 1, we need to flip it as 0. Let us do this. For 0, 0, 0, 0, we get as 1, 1, 1, 1. And further, for 1, 0, 0, 1, we get as 0, 1, 1, and 0. What I have obtained here, value number, that is 1110, it is what we have ones complement. Okay, it is ones complement of 00001001, which we had here. Okay, so which we have obtained here, it is a negative number of plus 9. Plus 9 is printed as this. What we have obtained here, it is printed as minus 9. Okay, this is what is ones complement. Here we flip all the bits, that is, if we have 0, we flip it as 1, and if we have 1, we flip it as 0. It's simple, we need not too much here. We simply flip the bits. We get ones complement. It is also a binary number, but we obtain it by flipping all the bits. Okay. Let us learn in depth what is ones complement. It is used in several places. It is used in representation technique that, as I said, it is used in computer systems. They understand in terms of binary numbers. No, so we convert into binary number. They understand ones and twos complement. Twos complement we learn at last. What is it? In ones complement we have unsigned and signed form. Both signed and unsigned form can be converted to ones complement. Different types of complement are possible for binary number. But ones and twos complements are mostly used for binary numbers. Okay. For when numbers we use mostly ones and twos complement. We can find ones complement by simply inverting the given number. That is what I said. Flipping bits is about inverting the number. We invert 1 to 0 and 0 to 1. Let us learn some more examples here. Ones complement of by number 1011001. We have bits 1011001. We flip each bit. That is 1 becomes 0 and 0 becomes 1. We obtain 0100110. What we did here, we flip each bit, so we get 0100110. This is what is ones complement which we obtain by flipping all the bits. Okay. Similarly, you can do it where we flip the bit in. Circuit representation we can do it by using NOT gate. Okay, here we have VNC. Finding ones complement of by number, we can implement logical circuit by using NOT gate. In logical circuit, how we implement ones complement? We implement using NOT gate. Okay, we not get for each bit. For each bit, we add a not gate. Okay, if we have 8 bits, we add 8 not gates. If we have 4 bits, we have 4 not gates. Let us say an example. Here we have 5 bits, so we have 5 not gates. Okay, if we have 8 bits, we have 8 not gates. Similarly, how many bits have that not gate? That number of not gates we will use to obtain one's complement. How not gate, what is the function of not gate? It inverts each number. If we provide input as 0, output in not gate will be as 1. If we have input as 1, output will be as 0. We have learned from truth table. Truth table of not gate is for 0 we get as 1, for 1 we get as 0. Similarly, one's complement we obtain by inverting each bit. That is what the function of not gate. And let us learn some more examples. One complement of 0, 1, 1, 1 is 1, 0, 0, 0. And one complement of 1, 1, 0, 0 is 0, 0, 1, 1. That is what we have done here. No, we have flipped each bit. Example, if I take input as 0, 1, 1, 1, I will pass it through a NOT gate. What will get? What will I get? I get as 0 becomes 1 and all these 3 ones become zeros. So I'll get 1, 0, 0, 0. It is what I required for one's complement. No, input of NOT gate represents one's complement. Okay, what we provide input, if we get the desired output, that is what represents one's complement. We need to simply flip all the bits. That is what we have done here. Now let us learn truth table. Truth table, it represents each input and output form in terms of tabular form. Okay. Have for example, if we have 4-bit representation, here we will have 4 inputs. We present each as A, B, C, and D. Corresponding outputs we get as W, X, Y, and Z. For A we get output as W, for B we get as X, for C we get as Y, and for D we get as Z. Okay. Now, since we have 4-bit, we combinations total physical combinations are 16. Okay, let us see the 16 combinations. First is 0000. Okay, we get as if we flip each bit, 0 becomes 1, 0 becomes 1. Similarly, we have 1111. For 0001, we get 1119. For 0010, we get 1101. Okay. Similarly, for 0011, we flip first 2 bits and next 2 bits. We get 1100. We can implement by not get, but we have truth table same. However, we implemented truth table will be same for both of the things. Okay. 0101, we get 1010. Next for 0110, we get 1001. We are flipping each bit here. 0111 is 1000. What is 000? We get the output 1000 is 8 till 7 we completed there. Now we are doing for 8. 100 is nothing but 8. Here we get 0111. For 9 it is 1001. We get 01190. For 10 we get 1010. We get output as 0101. We are flipping each bit. For 11 we get 1001. We represent it as 11 binary form. So output we get as 0100. For 12 we get as 1100. For in one's complement form we get as 0011. For 13 we represent it as 1101. In one complement form we get as 00190 finally. For 14 we get as 1110. If we pass through NOT gate, get the output as 000 and 1. Finally for 15 it is 1111. Output will become 0000. Okay. Here we are passing each bit through a NOT gate. So we get the output as inverted output. Okay. This is what our table is. Next, with midterm representation and K-map. What is midterm representation? Midterm representation is a specific product term. It represents a unique combination of inputs for a given Boolean function. It is a product term which represents unique combination of inputs for each of that function, Boolean function which have implemented. Okay. Here we represent each term as a product of sum of product. We get as SOP and POS respectively. SOP represented as sigma small m and POS represented as pi capital M. Here we are doing for SOP, that is sum of product. That is, we are adding each product terms individually. So we get as min term product representation. Let us see here. Okay, W is equal to sigma m of 0, 1, 2, 3, 4, 5, 6, 7. In last slide we saw no, where we get the output for as 1, 1, 1. Here we print it as min terms. We got as 0, 1, 2, 3, 4, 5, 6, 7. In all these places we got the output as 1. So we are printing as W equal to sigma m of 0, 1, 2, 3, 4, 5, 6, 7. Similarly for Hence we got the output in terms of output as maximum or 1 in the positions of 0, 1, 2, 3, 8, 9, 10 and 11. So we are represented as sigma m of 0, 1, 2, 3, 8, 9, 10 and 11. For z, y we got the high output in the positions of 0, 1, 4, 5, 8, 9, 12 and 13. So we have a minterm representation as here 0, 1, 4, 5, 8, 9, 12 and 13. Similarly for z we got as 0, 2, 4, 6, 8, 10, 12 and 14. In all these positions we got the output as high. High output means 1. So we print as minterms. Let us representation K map. Okay, what we'll get in K map representation. K-map we print is by as this. First we put the tabular column, and for each we print a product return product of sum. We present in K-map. First product is A bar B bar. Next product is A bar B. Next is AB. Next is AB bar. How did we get this? We got it by truth table. A bar B bar is nothing but 0 0. A bar B is nothing but 0 1. This is 1 1, and this is finally 1 and 0. Since K-map follows Karnaugh method, splitting of bits is difference between each bit is 1. 0 0 0 1 1 1 and 1 0. Similarly, we get C bar D bar, C bar D, CD and CD bar. What we had midterm representation of W. W we had sigma m of 0, 1, 2, 3, 4, 5, 6 and 7, right? So at all these positions we represent as 1. 0, let's say we have 1. It is first position we get as 1. 2 here, 3 here. 4, 5, 6 and 7. At all these places we get as 1. Rest all places we get as 0. So in K-map what do? We group all the ones together. How do we do that? We group together by using either a circle, a pair, a chord or an oct. We do by using pairing which possible combinations we get by that according to that we pair. Okay. First let us see if oct is possible. Yes, oct is possible. So we need to go for oct. We can't go for chord because in K-map we need to look for maximum number of combinations which we get. If we oct is possible, we need to do it according to oct. We shouldn't do it according to chord or pair, etc. We have oct here, so we do it by oct. What is the solution for oct here? C bar, D bar, C bar, D, CD and CD bar. They all cancel each other. Why? At all these positions we have 1, 1, 1 and 1. So when we simplify it, we they all cancel each other, so we will be left out with nothing. In column we are A bar, B bar and A bar B. If simplified we will get common as A bar. So solution of this oct is A. That is what is group 1 reference test. So solution of W is A bar. Understood, right? First we represent each midterm position. At all these positions we represent as 1. Since we don't have any don't care condition, so next we all do it as zeros only. So we group it according to oct. Answer we got it as A bar. That is what is answer of W. Next we look for X. What we have in terms of X? We have 0, 1, 2, 3, 8, 9, 10 and 11. Let us represent in K-map. We'll put here output in 0, 1, 2, 3 positions and finally in 8, 9, 10, 11 positions. Rest all positions occupy 0. Now let us group ones together. Okay. Now let us see if oct is possible. Direct oct is not possible. Let us see indirect oct. If we overlap first and last row, we get as oct. So let us do that. By overlapping, we get group 1. That is 1 1 1 and 1 1 1. If we overlap, we get an oct. So we specify oct as this. So let us simplify this oct. Here C bar, D bar, C bar, D, CD and CD bar. Again they cancel each other. Since all have high outputs, when we simplify they all vanish. So we get we don't get any of these terms in the answer. Now we are left out with A bar, B bar and A B bar. Why A B bar? Because since I have taken while overlapping, we have A bar, B bar and A B bar. Among these two, we need to search for common terms. A bar, here we have A, so only B bar is common. So answer for this group, that is group 1 is B bar. Okay. So answer for this whole K-map becomes B bar. So answer for X midterm representation is B bar. We had W as A bar. Now we have X as B bar. Now let us move on to Y. Y have midterm representation as 0, 1, 4, 5, 8, 9, 12 and 13. Now let us represent in K-map. At all these positions we need to specify as 1 or whole output. Rest all positions we need to specify as 0. In at 0, first, 4, 5, 8, 9, 12 and 13 we specify as 1. Rest all positions of the low output, that is 0. Now let us group together 1. Let us search if we have opt possible. Yes, we have opt possible here. So we group as opt. What is the answer now? So it is slightly different from previous two cases. Here A bar, B bar, A bar, B, A B and A B bar. They all cancel each other since they have all high output. They all vanish together. We are left out with C bar D bar and C bar D. What will get as common? Here C bar as common. So the answer for this is C bar. For the W we got as A bar, X we got it as B bar. Now for Y we got it as C bar. So let us move on to Z. What will you get for Z? Midterms is 0, 2, 4, 6, 8, 10, 12 and 14. We represent it as K-map as follows. Similarly, 0 we have here. Next 0, 2, 4, 6, 8, 10, and 10, 12 and 14. 0, 1, 2, 3. Here it has 1, 2 is here, 4 is here, 6 is here, 8 is here, 10 is here, 12 is here and finally 15 is here. So these all just occupy 1 and rest all we initialize to 0. That is, in rest all positions have output low output as 0. We need to group ones as it is. Let us search for direct dot. Direct dot is not possible. Here we need to overlap from this end to this end. If we overlap, we get between C bar D bar and C bar D, we get 10 oct. C bar D bar and C D bar, we get 10 oct possible. So we need to group according to an oct. Here it is only one group. Now let us simplify it. Here also A bar B bar, A bar B, A B and A B bar, they all cancel each other. So we are left out with C bar D bar and C D bar. Among these two, which is common? D bar is common. So the answer for this opt is D bar. Now let us do logical diagram. According to those midterms, we do logical diagram here. For A, what we get the output, we get it as Y. For each bit, I said right. For each bit, we implement a NOT gate. What if we do NOT gate? Inverts the input. If you have A as input, not give a plain NOT gate, we get A bar. For if you have B as input, we get B bar. For C, we have input C bar. For D, we get D bar. According to game apples, we got similar outputs, right? For W, we got as A bar. For X, we got as B bar. For Y, we got as C bar. And finally, for Z, we got as D bar. For W, X, Y, and Z, we got output as A bar, B bar, C bar, D bar. According to K-map. Similarly, for logical diagram is also got same thing. So according to this truth table, also verify for logical diagram. Finally, this is what is the conclusion. Logical diagram follows truth table of 1's complement. Now let us see what are the applications of 1's complement. Why do we need 1's complement? As I said, computer language may not always understand the codes we write. It only understands certain codes or certain forms of binary numbers. That is 1's and 2's complement. Here we have learned 1's complement. I'll briefly introduce about 2's complement. In 2's complement, first we do 1's complement and then to least significant bit we add 1. That is, if we have binary number as 0000, if we do 1's complement, we will call the bits. That is, we get 111 and 1. To the least significant bit, we add 1. That is 1111 plus 1 we add. We get 2's complement for that. So 1's complement is used for 2's complement as well. It is used to represent both signed and unsigned numbers. Uh, that is negative binary numbers in signed magnitude. It is also used in various arithmetic and operations, arithmetic and logical operations like subtraction, addition, etc. It plays an important role in representing signed binary numbers. Without 1's complement, computer can't understand signed binary numbers. So using 1's complement, you can present both +9 and -9, as I said earlier. So according to this, we are representing both 1's and 2's complement according to the system. Here we are learned about 1's complement. Hope you have got this. So first we learned what is one's complement, how to represent it, how to represent in truth table, how to represent in K-map, simplification of K-map, what are the applications, where it is used in computer systems, etc. Hope you guys learned a bit from this. Thank you.